Yeah, this paper appeared in Formal Aspects of Computing. There are references there, and the QR code takes you to the paper, which you may be able to get if your university or company allows. Anyway, this is joint work with my PhD student who's now a postdoc, Yuyan and Gidon Ernst. I don't know if Gidon is here. But anyway, so our goal is to combine the advantages of separation logic and region logic. So partly because we're interested in specification and verification, trying to figure out what's the best way to specify frame properties. And so we'd like to verify, this is kind of a goal that comes up secondly, programs that use both separation logic and region logic, sort of combine different libraries that are specified in different ways. And our approach is to translate both into some unified fine-grained region logic language that Yuyan invented. And we actually translate a subset of separation logic and a kind of extension of region logic called fine-grained region logic. And I'll introduce those as we go along. And we also show the translation preserves meaning. So we use intuitionistic separation logic because in a garbage collected language like Java, you don't want to necessarily have the exact heap as in classical separation logic. And region logic from Banerjee, Naumann, and Rosenberg was intended to be a kind of first-order equivalent of separation logic. And we'll see that that does kind of work out. And dynamic frames is a technique that you can use. It's often used with region logic or something like region logic, where you put regions into auxiliary or ghost variables, and it makes things very flexible, so you can dynamically decide what the region is. And that's used in the key tool and in Daphne. So to give an example and to give a little background about framing, here's a very simple, overly simple perhaps, class of cells where we have a constructor that sets the val field, which is private to the argument v, and a set method that does the same kind of thing. It sets the val field to v. And so we might have a client that creates a couple of objects of this cell type and sets both of their val fields to 5. And then what we'd like to do is to know that after we set the second val field, that the first one is still preserved. It's still 5. So we'd like to preserve the values of these assertions through method calls and constructor calls. I'm just going to focus on method calls in the following. So both of these region logic and separation logic have a way to deal with this called the frame rule, which is a rule in logic that you can see at the bottom here that shows if we have a statement S and a precondition P and a postcondition Q, and in region logic, this epsilon is the right frame or the region of threatened locations that could possibly be changed by S. And you want to preserve this other assertion R through the execution of that. And in region logic, the idea is that you can do that if a region that frames this other assertion, delta, is separated from epsilon. That's something you can prove directly in region logic. And you get to use the condition that the precondition is true to do that. And in region logic, you write specification. You explicitly say what the frame condition is. This is the right effect of this method set, which says that it changes the val field of this object this, essentially. And in separation logic, things are a little more elegant. I'm sure a lot of you are familiar with this. You basically just say the precondition. You have this points to assertion that gives the method access to the val field of the this object. And there's this separating conjunction, which you can use in the frame rule, that says that if you want to preserve R across this statement, you have to show that it's separated from the assertion A that is the precondition. and also the postcondition. And then there's some side condition about the free variables. So that's very elegant. And at various times, we'd like to use the advantages of each of these kind of ways of doing things. However, there are some disadvantages. In separation logic, it's difficult to apply the frame rule if you have sharing in your data structure. So if you have something like a directed acyclic graph, you can specify it in separation logic. You would say something like a DAG is something where the left field and the right field are separated from each other, and you have DAGs in the left and right pieces of storage. But this use of regular old conjunction means that they don't necessarily have to be separated. And so that makes it so you can't directly apply the frame rule of separation logic. In region logic, you can deal with those kind of things. There's a way to do that in the logic. However, when you have separation, it works well in separation logic, that doesn't work so well in region logic, because you have to write something like this, which says that you have an L and an R field that point to I and J, and those are both DAGs, and those regions are all disjoint from each other. This exclamation point is a disjointness assertion in region logic. So that's kind of a disadvantage of region logic. And our contribution, the way we try to work things, is to have this other logic called Unified Fine-Grained Region Logic, or UFRL, that unifies reasoning in supported separation logic and fine-grained region logic. And this logic, like region logic, can be encoded into first-order logic, which was one of the main goals of region logic's design. So you can use it with SAT solvers, for example. So automation, it works a little bit easier than it does for separation logic. So the goal after we started doing this was to be able to use different methods from different libraries specified in different formalisms, so you could interoperate them together. And the way that's achieved is by extending region logic. So we extend region logic by making it fine-grained, first of all, by having regions as sets of locations instead of just sets of objects. That makes it technically a little bit easier to specify points to assertions and the translation of those. And then the main thing, though, is to come up with a syntactic footprint function to specify the read effects of things in region logic. So that gives us this unified fine-grained region logic, which extends region logic. And we can translate supported separation logic into that in a way that I'll show you later. So what I'm going to show you now is a little bit about unified fine-grained region logic, and then I'll talk about the translations, or really the embedding in the translation. So UFRL has heap-free expressions, these E things, and also region expressions. They're both kind of something like expressions, this F thing, which you can use on the right-hand side of an assignment. And these expressions like numbers and variables and null are all completely pure. They don't involve the heap at all. Region expressions, they can be stored in variables. There's also the empty region, a region just containing a particular field of a particular object, a region containing all the fields of some object. And we know the types of things so that this makes sense. And then this is the union of two region expressions. This is a conditional region expression, so just like the question mark colon operator in C, C++, or Java, if E is true, then this denotes the region 1, otherwise it denotes the second region. Alloc is the region that's the domain of the entire heap, so it's all the allocated objects, fields. And then you can have Boolean expressions, which can involve these two heap-free expressions, equals and not equals. And you have this syntax of assertions, which is kind of inspired by the supported separation logic fragment that we want to deal with. Because you can see we don't have disjunction, and we have only a limited kind of existential quantifiers, and we don't have negation. So you can have Boolean expressions and implications of Boolean expressions to assertions. And these are like the points to assertions in separation logic. They just say that some field has a particular value. You can have conjunction. This is a subset of region expressions. So RE1 is a subregion of RE2. This is disjointness of region expressions. And this is a particular kind of existential quantifier that has this sort of one-point rule that you could apply to it. So the semantics are pretty standard. The values in the language UFRL are just Booleans and objects, which you can think of as just an infinite set of integers. Null, which is a special kind of null object. The integers and sets of locations, which are the regions, the denotations of regions. And the store, as usual, maps is a finite mapping from variables to values, and the heap maps locations to values. And locations are just pairs of objects and field names. So, for example, after you make v1.2 a new cell containing 5 in its val field, the store maps v1 to some object, let's call it O1, and the heap maps this pair of O1 and val to the value 5. And the meanings of statements are functions from statements, and states, which are pairs of stores and heaps, to either a state or bottom or this distinguished error result. So expression evaluation in UFRL doesn't involve the heap at all, just maps the store, a kind of expression-like thing and a store to a value. So for variables, you just look them up. For numbers, it's the usual thing. For region expressions, if the variable in x.f is null, then you get the empty region. Otherwise, you get a region containing that single location. And for the if then else, you get if the test expression is true, then it's the denotation of the first region expression. Otherwise, it's the denotation of the second. And then for assertions in UFRL, assertion is valid in a particular state. This x.f equals e is valid if the x.f denotes a location in the domain of the heap, and the heap maps it to the meaning of that expression in the store. And things like all the other binary operators are kind of like this. This is the disjointness. So RE1 is disjoint from RE2 if the denotations are disjoint as regions, as sets of locations. And you just use induction for and all the other things like that. Union, for example. So we specify statements in UFRL with both read and write effects. And the statement can read from whatever it's allowed to write and also what you explicitly allow it to read with this delta that comes first. So you have these quintuples. The thing at the end is what's allowed to be written, the region that you can write, and the thing at the beginning is what you can read. We take a partial correctness interpretation of these quintuples, but it's fault avoiding, like separation logic, in that it's invalid if the meaning of the statement in a state that satisfies the precondition denotes an error. So it's not allowed to go wrong in that way, but it could go into infinite loop. And then the more interesting bits about UFRL is that there's a static way to figure out what it reads off the heap and what its footprint is. So what the read effects of a assertion are is given by this EFS or effects function. So the read effects of a variable is just that it reads x. This is a sort of region effect expression in UFRL, and the effects of region x dot f, or just that it reads x. We don't need to know what the value of f is to know what the region is. We just need to know that that variable is not null, and the same goes for x dot star. If you have something like x dot f equals e, however, you have to read both x and x dot f because you need the value in x dot f to compare it to e, and you have to recurse to get the value of e, which would usually be empty. And then for an implication assertion, that's translated into this kind of conditional region expression or conditional reads effect. So that if B is true, then we take the effects of B and the effects of the thing P here in that case. And otherwise, it's the effects of B, and that's always going to be the empty region. It's reading from the empty region. So these are just the heap effects. And then the axioms for assignment are basically simple, that it's just what you would expect, except we have to figure out the read effects to go with the beginning. So the read effect is that it reads from the expression on the right-hand side of the assignment statement in every case. So that's not terribly interesting. And then that's enough to allow you to do stuff in region logic, and we can validate this frame rule in separation logic. Unified fine-grained region logic says this. So the idea is that whatever this assertion R that we're trying to preserve has to be framed by some region eta, and eta has to be provably disjoint from epsilon, which is what's threatened by the statement S. So you have to be able to prove that separation, which is part of the region logic stuff, under this precondition. And so we don't allow those to overlap, for example. So with all that, it's pretty trivial to embed region logic into UFRL. We basically have used the same syntax, and so the assertions translate over directly. We just basically have to fill in the reads part. So in UFRL, you have to specify for a method, you have to specify what it reads, and we just say it can read the entire heap. And that's good enough for making these assertions, these quadruples into quintuples. We just say it can read anything. And there's some side conditions that I'm omitting. You can see the paper. And the encoding of inference rules is basically just the recursion as you would expect with this as the base case. And so that works out very well. And so we have a couple theorems about this embedding of region logic into UFRL, which are just kind of what you would expect, that an assertion is true in a particular state in UFRL if and only if it's true in that state in region logic, or fine-grained region logic, actually. And then the more interesting thing is that if you can prove that this quintuple holds if and only if you can prove that the fine-grained region logic's quadruple, which doesn't talk about the read effects, holds. And that's just as you would kind of expect, because we only allow we allow it to read anything at all, and which is really the semantics of the fine-grained region logic quadruples. So that's all sort of just stuff you have to check. The interesting part is about separation logic. So just a quick reminder, separation logic, there's these points to assertions, which are something like x dot f points to e, and that's true if the location x, the value of x and f, the f field, is in the domain of the heap, and the heap maps that to the denotation of the expression e. And this, again, is intuitionistic separation logic, so we don't care that the heap might have more stuff. So the heap could actually be bigger than just this location. That's perfectly fine. And then separating conjunction it's kind of got an implicit existential quantifier. So you find two heaps that each of which makes one of the assertions true, and those have to be separated or disjoint from each other. So, and they have to combine, they're disjoint and they combine to form the original heap. So you have to be able to split the heap into these two parts or partition it and then get these two assertions to be true. That's the interesting thing about separation logic, is that it's got this kind of search or existential quantifier in it. And conjunction is very similar, except you don't have to split the heap. And similarly would be for other things like that. For example, implication. So the frame rule in separation logic, you might remember, looks like this, just that we have to separate the assertion we're trying to prove from the precondition and the postcondition. And what is allowed to be read and written is everything in the precondition. So the precondition kind of describes this miniature heap, and that gives the command or the method permission to read and to write from that part of the heap. Now, supported separation logic is a sort of subset of separation logic that there's always a smallest heap chunk that makes that assertion true. And this is why there's not disjunction, for example, in supported separation logic, because with the disjunction, you'd be able to have one heap chunk that makes the left-hand side of the disjunction true and one heap chunk that makes the right-hand side of the disjunction true. And then there wouldn't necessarily be a smallest one that makes them both true. And this is required for hypothetical reasoning, and it's also the kind of subset of separation logic that most tools deal with. So most tools don't deal with unrestricted existentials or disjunction. And so we have the same kind of set of assertions that we've talked about before for UFRL, and the same kind of restricted existential quantifiers here. And then to encode that into UFRL, basically we have two parts. We have a translation function that translates assertions from the syntax of supported separation logic into the syntax of UFRL. And we have this footprint function, FPT, which takes the footprint of an assertion in supported separation logic and returns a region expression. And that's the tricky part. So once you can do that, you can do most everything. The translation of the assertions is pretty straightforward, but the trick is getting to have this static footprint function that does the right thing. So here's what that footprint function looks like. And on the left-hand side are assertions in supported separation logic, and on the right-hand side are the region expressions that result from calling the footprint function. So an expression, because it's pure, doesn't access the heap at all. A points to expression accesses x.f because it's got to get the value of x.f. Something like B implies A it translates into a conditional region expression. This is why we need the conditional region expressions, essentially, is to make this work out. If B is true, then it's the footprint of the assertion A, and otherwise it's the empty region. And the footprint of A star A2, A1 star A2, is just the union of those two footprints. And it's the same footprint as for the conjunction. So it depends on whatever is used in either of those two sub-expressions. Sub-assertions, I should say. And then this one, it's the region y.f, which is substituted for all the free occurrences of x in the footprint of A. So the idea of this is to flush the existential variable out of the quantifier. the translation is pretty straightforward. We translate the expressions basically identically because we've set up the language to be that way. And equality expressions, you just translate each side and put an equal sign in between them. And for the points to expressions, you just use that x.f is equal to the right-hand side. The implications translates into implication of the translations. And the interesting part is the separating conjunction, which translates into a conjunction in the UFRL, also conjoined with a disjointness. So this says that the footprint of A1 has to be disjoint from the footprint of A2. And you might think that's kind of weird because this is definitely static, but of course, in separation logic, that has to be decided statically too, that there exists something like this, because we're going to be doing all this reasoning statically. So that does work out. And the conjunction just translates into a conjunction of translations. And because there's a separating conjunction in the existential, that translates into kind of what you would expect, plus this disjunction of regions. So the y.f has to be separated from the footprint of the assertion that's here. So we were able to prove, and this was done, the first one of these was done formally using this Karlsruhe interactive verifier, that the translation of assertions in separation logic preserves into UFRL, preserves the meaning. So in a given state, an assertion is true if and only if the translation is true. And then we also proved that the supported separation logic axioms for their kind of Hoare logic and each translated inference rule is admissible in the UFRL proof system so that the proofs translate. So let me talk a bit about related work. So there's been several ways that people have looked at framing. So ownership types are one way, and they're very nice for layering and modularity, but they make it difficult to specify and verify sharing. The boogie methodology makes that a little bit easier. It's more expressive in that respect. In fact, ownership transfer works better, of course, but there's more specification overhead. And the dynamic frames is really flexible, but the verification requires second-order logic in general. So that was part of the inspiration for region logic. And we were inspired by this paper of Parkinson and Summers that translates separation logic into chalice, which is a different logic. So it doesn't directly do the same thing as what we do, but we adopted a lot of their ideas for our work, and it was pretty inspirational. Other work on region logic and separation logic I've already mentioned, the paper on region logic, and there's been continuing work on that, and this is the intuitionistic separation logic that I mentioned before. So in the future, we'd like to work on information hiding and abstraction, and Yuyan Bao in her PhD thesis started work on encapsulation for behavioral subtyping, which is the way we think we need to solve this to get a modular treatment of behavioral subtyping. But that work hasn't finished yet because she went off to do a postdoc on some other stuff. So I'm happy to take questions. Oh, but after my summary, which is that we unified supported separation logic and fine-grained region logic, and the fine-grained region logic is embedded in unified fine-grained region logic, and you can translate supported separation logic faithfully, preserving the meaning of assertions and provability. So, any questions?
So, hello, my name is Theodoros Kasampalis, and in this talk I will present Daniele, a language that we designed for the blockchain. So first I will give a brief overview of the blockchain and the smart contracts. A blockchain is a data structure that you can imagine it as an append-only ledger. Typically, it is used for synchronization in distributed networks, and there it is used as a log that records all the transactions that are going through the network. And each node of such a distributed network maintains a local copy of the blockchain, and the local copies are being updated based on a consensus algorithm. So many blockchain networks allow code to be associated with the accounts that are on the network, and such code is called a smart contract, and it is typically executed when the account associated with it is receiving a transaction. And the smart contract code is also stored in the blockchain on those networks, and because of that, it is public, because every node has a local copy of it, and also it is immutable because the blockchain is append-only. So one of the largest blockchain networks that are there today is the Etherium network, and this is the largest one that supports smart contracts. These days in the Ethereum network there are more than 500,000 daily transactions, and these transactions typically transfer a cryptocurrency called Ether between accounts. Ether today has a market cap of 18 billion United States dollars. So as I mentioned, Ethereum supports smart contracts, and these contracts are written in a stack-based assembly language and they are executed using a virtual machine called the Ethereum virtual machine, or EVM for short, and also the EVM term is used also to describe the name of the language itself. Unfortunately, in the recent years, there have been various exploits on EVM smart contracts that have resulted in losses in the range of tens of millions. I list here the three largest incidents, and there is a more detailed description for each of those three in the paper, if you are interested. So, as a response to that situation, the Ethereum community has adopted KEVM, which is an executable formal specification for the EVM language. The KEVM specification was developed with the K framework, and because of that, the K framework provides an auto-generated and correct by construction implementation for the language, and also in the same way it also provides a deductive verifier. And that verifier has been used and is being used successfully to verify real-world Ethereum smart contracts today. So, given this situation, in this work we decided to go one more step forward and actually design a new language for the blockchain that will avoid all the pitfalls that made EVM insecure. This new language we named Yele, and it is also it's similar in assembly language that is designed to serve as an alternative to EVM. So for the design of this language, we took lessons from the KEVM effort. So we also designed Yele from scratch as a formal specification first, and we didn't do any work to get an implementation. We used again the K framework to derive a correct by construction implementation from the formal specification that we wrote. And we set four main design goals for Yele. First, security. So we specifically wanted to make various known exploits of EVM smart contracts inexpressible in Yele. And we also, of course, included all those exploits, all those three exploits that I showed in the previous slide. We made sure that those are inexpressible in Yele. Our second goal, design goal, was formal verification. So we knew from the start that we wanted to verify Yele code. So we designed the language with features that make automated verification easier. Third, we wanted the language to be human readable. So even though it is an assembly language, we thought it is important that the smart contract code to be readable by humans in the form that is being executed, so in this assembly language. And finally, the language should be deterministic, and that is true for any smart contract language because they should be fully deterministic to allow replaying transactions that include code execution when the local nodes want to replay those transactions to update their local copy of the blockchain. So with all that, let me walk you through the main features of the YELE language. So here you see a contract. This is the main code unit in YELE, so this is a YELE contract. And as you can see, a contract contains some global variables and some public and private functions. So when an account is created on the network, we can associate one or more YELE contracts with the account to serve as the smart contract code for that account. And there are two ways to do that, to create an account and associate code with it. So the first way is manually. There is a creation transaction that one can post to the network, and that creation transaction creates the account, and as an additional argument for that transaction, one can provide code, one or more YELE contracts to become the smart contract code associated with the account. And the second way is dynamically while executing smart contract code. So while executing smart contract code as part of any transaction, if there is a YELE instruction created, if this instruction gets executed, what it does is it posts a creation transaction on the network to create a new account, and the instruction create also accepts as arguments one or more YELE contracts to associate with a new account. Now, specifically for the second way for account creation, we do not allow dynamic generation of smart contract code. Now, to be more clear, so the YELE code that we pass as an argument to the create instruction to associate with a new account cannot be dynamically generated at that time. So it couldn't be, for example, it couldn't be code that is being dynamically generated by parsing a string or some binary data. Instead, the only thing that you can give to the create to associate with new accounts is YELE contracts already associated with the creator account. So unlike, and that is not the case for EVM, so unlike EVM, YELE enforces that the only way to introduce new smart contract code in the blockchain is in an offline fashion, using the first way, using manual creation transactions. Another thing that is associated with each account in a blockchain network is the account storage. So this is an unbounded sparse array of arbitrary precision signed integers. So it maps any kind of integer to an arbitrary precision signed in index to an arbitrary precision signed integer value. And the contents of those storage are persistent throughout the account's lifetime. So to make it easier to access this storage from YELE, we allow some named global variables to be used in place of the indices, of some indices. So as you can see here in this example, the creator name is used for index 1, for example, and if we want to load the contents of index 1, we can use the YELE instruction storage load, and there is also the storage store instruction to store data in the account storage. Next, let me talk a little bit about the functions that are contained within a YELE contract. These functions can be public or private. Private functions can only be called from code within the YELE contract. The private functions can only be called within the contract. Public functions can also be called from code of another account, of another smart contract associated with a different account. And the signature of the function specifies the name and also the number of parameters that it accepts. The control flow within a function uses labeled basic blocks and conditional or unconditional jumps to those labels. And we do not, unlike again EVM, we do not allow dynamic jump targets. So any possible target of a jump should be clearly statically labeled in the code, like in the example. Finally, let me talk a little bit about the function, how we call functions, specifically how we do the public function call. So for calling a function of another contract. So this we can do with the instruction call at, and when this instruction gets executed, it posts a transaction to the network. as you can see in the example, the arguments of this instruction involve the name of the function that we want to call, and also an address of the account that is associated with a contract that contains this public function. And also, as part of the arguments for the public function call, we can pass this value parameter. We can pass an amount of ether that we want to send to the account that we are calling as part of the transaction. Another distinction with EVM regarding function calls is what I call in the slide no delegate call functionality. So EVM provides a specific type of call, of public function call, namely delegate call, which will call a function of a different account, but when the function executes, it will execute in the context of the caller, not the context of the callee. And EVM uses that the trick so that it can enable code sharing. So there are some accounts that are associated with some library code, and this code can be accessed through a number of APIs, so a number of functions, public functions that other accounts can call. And now, if my smart contract wants to use like the library functionality, it can post a delegate call to the function that it wants to use, and then this function, when it will execute it will, for example, it will update the caller's storage, for example, instead of the callee's. So this feature has proved to be very insecure, and in fact, one of the three largest exploits that I mentioned before is related to this, is an exploit related to this feature. So we completely omitted that feature, and we still have a solution for Yele to avoid code deduplication, to enable code sharing, and more details you can find in the paper. But it has to do with that limitation that I mentioned before, that all the code needs to be manually introduced into the blockchain. There is no dynamic call generation. This feature enables us to share code in a different way without delegate call. Finally, a brief mention of how Yele instructions look like. So they are opcodes that have a specific number of arguments and return values. And also some of them are some built-ins, we call them intrinsics. And these ones, they are, if you want to use them, you call them like a private function call, similar syntax to a private function call. The language is register-based instead of stack-based. So, and we provide an infinite number of virtual registers available to the function. So like, in the instruction above, in this example, there are two different virtual registers that we can give them any names that we want. And the data type of all of the values that are propagated through the Yele program is arbitrary precision signed integers. That's also another difference from EVM that uses only fixed precision signed integers with different bit widths. This is a quick overview of the language. Now let me also do a very fast overview of the formal definition that we did using K. So there are three parts that are involved in this definition. The first part is the syntactic productions that define the syntax of a Yele program. This is an example of how we define the syntax of the Yele contract specifically. The second part is the specification of the execution state that a program can be at any time during runtime. And to do that, we use a construct called the K configuration. This is, as you can see from the part, this is a part that we saw part of the configuration, K configuration for the execution state in Yele here. And you can see it looks like an XML tree with cells and subcells. And finally, the third part, that may be the most important, is the transition rules. So these transition rules are rewrite rules. The left-hand side is a pattern over those configurations that are shown in the previous slide. And the right-hand side explains how to rewrite a matched configuration, a configuration that matched the left-hand side, how to rewrite it to do a step, to progress the execution. Okay, so So as I said, using this formal specification, the K framework allows us, the K framework by itself allows us to auto-generate a couple of various useful tools, and the first one of those is this deductive verifier. I want to make sure that you understand this is not something that we had to do anything. We just, after specifying the language, this is auto-generated for us. And every time we want to change something, for example, while developing the language, if we want to change something in the design, the change propagates to the deductive verifier and the other tools that I mentioned automatically. So this deductive verifier is complete. It can prove a modular domain reasoning oracle, Z3 specifically for this case. It can prove any reachability property about a ELE program. And yeah, we used this verifier to actually verify a handful of ELE contracts, real-world ELE contracts. But before I show you an example, I want to go through some of the features of ELE that make writing this like verification claims that we want to prove, writing those, making writing those easier. So, and I will compare and contrast with EVM. So, first, as I said, the ELE has only statically known jumps. So, the target of a jump is statically known, is what I mean here, and that allows us to easily modularly write some reachability claims about that will cover, we can easily cover all the possible flow, control flow of a code snippet of ELE. While EVM allows dynamic jumps, these dynamic jumps means that the target of the jump could be computed during the runtime, and that makes it considerably harder to write this kind, to cover all the control flow easily and modularly with reachability claims if you want to do a proof about an EVM contract. Another feature, as I said, another difference is that our language, ELE, is register-based instead of stack-based, and that makes it so that we don't have to worry about overflow for the operation stack that the EVM implementation is using to execute the stack-based instructions. Thirdly, as I showed again, we have a well-defined ABI for how to call functions in ELE that is part of the semantics. Unlike that, EVM does not have such an API that is part of the semantics. There is an encoding-based ABI that the community uses, but it's not enforced by the semantics of EVM, so it's not guaranteed that a contract will use this call ABI, which makes it really hard to do to prove verification claims that involve function calls, public function calls. We don't have this issue. And finally, the reason we chose arbitrary precision arithmetic instead of fixed precision is, again, that when we want to verify a ELE program, we don't have to worry about the cases of arithmetic overflow and what they will do, because arbitrary precision by default means there are no overflows. So, yeah, here is an example of a reachability claim that we wrote for the ERC20 contract. This is a very popular contract that the EVM version of it is used in the Ethereum blockchain right now. This contract provides functionality for maintaining and exchanging tokens, and it's widely used in the Ethereum blockchain right now. So yeah, this reachability rule, we want to verify that when a successful transfer of a balance happens, then the balances of the sender and the receiver are updated properly. This is what this rule does, and you can get a feel of how it looks like to write verification claims for ELE. Moving forward, two more tools that we also get for free from the specification when we use K framework are this interpreter and also a well-formedness checker for ELE contracts. And these two tools combined comprise the ELE VM, a virtual machine that can execute ELE code. So essentially what we do here is we get the implementation for the language derived automatically from the specification for free. So another component in order to have a functional ELE blockchain is an Ethereum client, and for that we use the Mantis Ethereum client. So what an Ethereum client does is it's the software that is installed in any local node of the network, and it receives and sends transactions to the network. So as I said, we used the Mantis Ethereum client provided by IOHK. This is a client that works for the EVM-powered Ethereum network, but we modified it so that it can work with Yele. And there is a relation between the virtual machine and the client. So the client, when the client receives a transaction that requires execution of smart contract code, it will invoke the virtual machine. And the virtual machine, when it executes, it needs to execute some kind of building that requires knowledge of the network state. It will query the client. So these two work together. And by combining them and with the support of the company that also provided the Ethereum client, IOHK, we generated a testnet that uses Yele VM, that uses Yele, and this testnet is live right now, and you can upload contracts and post transactions and play with Yele if you want. There are also more details about how to find it in the paper. And the final piece of software the final tool that we developed for Yele, that I will talk about today, is a compiler from a very popular high-level smart contract language, the Solidity language, to Yele. So as I said, Yele is an assembly language, so its main purpose is to serve as a compilation target for high-level languages, and we wanted to make sure that it's a practical language for that. So we took Solidity, that is a widely used smart contract language that people program in, and we created a compiler to Yele for that language. So there is already an existing EVM compiler, Sol-C, that is actually used for real-world contracts that are deployed right now in the Ethereum blockchain. So we started from there, and we wrote a new backend for Sol-C that compiles to Yele instead of EVM. And we use the same test suite that Sol-C uses to test the EVM backend to also test the Yele backend. So by doing that, there are some differences in the flavor of Solidity that the two backends accept. So for example, one difference is, since in Yele we have included arbitrary precision integers, we decided that it would be nice to also expose this feature to the Solidity programmer. So we enhanced the Solidity that you can write for the Yele backend to support arbitrary precision integers. Another difference is this delegate call functionality of EVM. This is exposed to the Solidity programmer also in Solidity by building, but since we don't support something like that, like the Solidity flavor that you want, if you want to use Solidity and compile it down to Yele, you shouldn't use this building. It's not going to work. And there are other similar differences, like around the same lines. Not a lot of them, but there are more details in the paper again. And I want to mention also that this Solidity compiler we had to implement manually. There is no way to auto-generate something like that. Excuse me. So finally, I want to talk a little bit about how we evaluated our effort. First of all, how we made sure that our compiler is correct, or how we evaluated how correct it is, let's say, and also how we evaluated the performance of the VM. So what we did is, as I mentioned before, we took the test suite that the Solidity to EVM compiler is using. This test suite contains more than 1,000 unit tests and also 5 real-world Solidity contracts, including the ERC20 contract that I mentioned before. And also the test suite, also for each one of those tests or contracts, it has a number of transactions that when you run the test suite, the transactions are executed, and then the test suite verifies that the result of the transaction is correct. All of these transactions, of course, include like executing code, smart contract code. So we took all of these unit tests and contracts in Solidity, we compiled them to Yele, and for that step we had to modify some of the contracts to make sure that the flavor of Solidity is appropriate for compiling it down to Yele. Then we took the Yele binaries, we deployed it to our testnet blockchain, and we executed all the transactions that are part of the test suite and verified that they work correctly using our VM and the modified Mantis client and Ethereum client. And here are some numbers. So in all of those numbers, higher is better, and specifically higher than 1 means we have an improvement. Lower than 1 means that we have a regression. So yeah, the first experiment we did has to do with binary size. So what is the size of the binary when we compile the Solidity code to Yele or EVM? So if you see here, there is a discrepancy. For unit tests, we get an improvement, so that means that we get the average size is lower, but for large contracts, we get a regression, so the average size is higher. So the explanation for that is that in general, what we expect, because Yele is a register-based language, is that the binary size will be smaller because a register-based language doesn't need to have all of these stack manipulations instructions that you see in a stack-based assembly language, that push and pop values or duplicate values in the stack, move around values in the stack before applying an operator, and so on and so forth. And that's why the unit tests, the size of unit tests is decreased. Now, that should be true also for large contracts, but then when we have a considerably large piece of code, and the fact that our compiler is completely naive, it doesn't include any optimization at this point, shows, and we believe that we can actually make this discrepancy go away if we actually implement some very simple optimizations in our compiler, for example, dead code elimination. When it comes to execution time, what we did is we compared the execution time of the transactions on the LVM with the execution time of the same transactions on the KEVM. And as you see, in both cases, we have a slight speed up in both for the transactions on unit tests and for the transactions on large contracts. Just to give you a perspective, the KEVM execution time, average execution time, is in the region of 10 times slower than the C++ optimized implementation of the EVM. So our LVM would be more or less 10 times also slower from an EVM implemented C++. And yes, this concludes my talk, and I'm happy to take your questions.
Good afternoon, everybody. My name is Genc. I'm from TU Munich. I'm glad that I'm presenting in today's symposium, and together with my supervisor, Diego Marmsoler, who is also in the audience, I'm going to present APML, which is an architecture-proof modeling language. And this is the content of today's talk. I'm first going to talk about architecture-based verification and the problem that we wanted to address. Then I'm going to talk about APML, implementation and evaluation, and at the end I'm going to give a conclusion. So let's dive into architecture-based verification. So nowadays, software systems become increasingly big, and as they become increasingly big and components enter the architecture or they leave the architecture, they become difficult to verify. So compositional verification can be applied to address this problem, and how this works is that it divides the verification of single components from verification of the overall architecture. And architecture-based verification is an instance of compositional verification, in which we have two steps. In the first step, we come up with contracts for single components, and we try to verify their behavior respecting this contract. And at a later stage, we combine those contracts, and with the combination of those contracts, we try to verify the overall architecture property. And yeah, for the first part, to verify the components themselves, it's actually not difficult, as they are rather small, and model checking can be applied, such as, for example, NewXMV. But our work was more focused on this part. So when we combine the contracts and we want to verify the overall architecture property, then we need to apply reasoning. And to do reasoning manually is actually difficult, and it requires quite some work. So for this case, one solution that one can do is to use interactive theory improvers, such as it is with Isabel. So there we come directly to our problem that we have a gap here between users and Isabel, because usually interactive theory improvers are quite complex and they require quite some expertise. And like our goal was to fill in this gap and to basically have an intuitive way for users to come up to write these contracts and to kind of cover this whole thing. So what we introduced is we worked on APML, which is an architecture proof modeling language. And what we wanted to do is that here we have Isabel code, and here we have the users. So basically here in the middle we wanted to introduce something that makes it intuitive for the user to model the system and to model the contracts and connect those to one another. So with APML we made it possible for the user to write the contracts and to combine those in a similar way to a message sequence diagram. I will shortly give you an example on how that works, but first I'm going to give some definitions which are important. So two of the maybe most important definitions that we have is the definition of an architecture and a contract. The architecture is a pair of disjoint set of interfaces and the connection between inputs and outputs of interfaces. And the contracts for an interface is a triple TGGRD, which are basically a trigger for a contract. Then we have a guarantee, and then the duration of how much time that takes. And for the contract, we have additional constraints. We have the constraints that the time point of the first trigger is 0. Then all the triggers are ordered by their time points. And finally, the guarantee happens. So, the guarantee actually happens after the last trigger. And with this being said, let's check an example. Here, for example, we have an architecture. And this architecture, this is the architecture of a reliable adder, which, basically what it does is that it accepts two inputs in the dispatcher components, and then at the end, it spits out an output at a specific time point, which is the sum of these two inputs. And how the architecture works is that we have two adder components, adder 1 and adder 2, and adder 1 and adder 2 calculate the sum of the two numbers in different durations. So let's say, for example, adder 1 guarantees that that it yields the sum after 5 time points, and adder 2 yields the sum after 4 time points. And then they pass the result to the merger component, and the merger component then gives a final result. So this is the overall architecture, and these here are the contracts. So here you can see that these components have only one contract each, and then we have the merger component, which has actually 3 contracts. And here it has 3 contracts because we did also contracts for cases like what if the adder 1 yields the result first, or what if they yield the result equal. So that means that we have 3 cases when they spit the result out at the same time, or this earlier, or this one. And in this side, then we have the overall architecture contract. And with this, we try to verify the architecture property. And this contract is quite similar to normal contracts, so it also has a trigger, a guarantee, and a duration. But what differs here is that we also have proof steps. So this is the approach how we do this. For each architecture contracts, we need to have proof steps, and all of these in combination then form the overall proof. So what is a proof step? A proof step for an architecture and corresponding contracts for its interface is a for tuple, which has a time point, which is a natural number. It has an architecture state at that specific time point, which is basically the output of that interface. Then we have a rationale, which is a reference to a trigger for a component. And then also a possible empty sequence of references, that means that from a proof step you can actually have references which might be proof steps from the past or another trigger from the architectural contract. So this is an example of how a proof step would look like. For example, here we say at time point 5, have x plus y in the output of adder1 component by applying the add1 contract. And we refer to previous proof step 0 with connections between inputs and outputs of the dispatcher component and the adder1 component. And basically then the overall architecture proof is then the collection of those proof steps. And in the end, the last entry implies the guarantee of the architectural contract, and here we also have some constraints. So for each proof step, we can reference, as I said, a trigger from the architectural contract, or we can reference a previous proof step. Then the time point of the reference entries respect the time points of the triggers of the rationale. That means that the triggers and the references can happen at different time points, but the thing here is that they have to be in the same intervals. The reference entries imply the corresponding triggers of the rationale. The time of the current entry respects the duration of the rationale. And last but not least, the guarantee of the rationale implies the current state. So to combine these definitions then with our previous example, this would be an architectural contract. So we say that we have a trigger here that says, okay, input 1 is x and input 2 is y at time point 0. And then we want to guarantee that the merger output is equals to x plus y at time point 7. So we add the first proof step, which happens at time point 1. And the state here is that the outputs of the dispatcher components are equal to xy. So xy here and then xy here. And here, note that we reference directly to the contract of the dispatcher. And we reference the first trigger of the architectural contract. And then we go on, we add the second proof step. Then here we say that, okay, at time point 5, we have the result that the output is equal to x plus y. And we reference the add1 contract. And for additional references, we have that we reference the proof step 1 by adding also the connections between the inputs of adder1 and the outputs of the dispatcher. And so on, we continue with adding proof step 3, which is quite similar, and also the proof step 4. And note that in the proof step 4, we have the final state. So this is then the output of the merger is equal to x plus y. And we reference here the previous proof steps 1 and 2. And as I said in the beginning, that our goal was to kind of give the user the possibility to model this in a similar way to a message sequence diagram. This is how it would the whole proof would look like in the message sequence diagram. So here we would have the first proof step. So here we apply the dispatch contract, and we have the inputs and the state at the duration n plus 1. And then, we basically just add the other proof steps. So the add 1, then we have proof step 3, and then lastly the last proof step. Our language is also sound and complete. For soundness, we have the following theorems. So, given that an architecture Fn and the corresponding contracts for each interface, such that the behavior of that interface satisfies the contract of that interface. If there exists an architecture proof for an architecture contract, we have that the composition of the behaviors satisfy the overall architecture contract. And for completeness, given an architecture A and corresponding contracts for each interface, for each architecture contract such that all possible behaviors satisfy the architecture contracts, there exists an architecture proof for the architecture contract. And we also have the proofs for those. Whoever is interested can read, can find these in the technical report of our paper. Next, I'm going to continue a bit with implementation and evaluation. So this is how APML looks like. Here we wrote the architecture contract for the whole reliable adder example. Here we have how the triggers are written, the guarantee, the duration, and then lastly we add all the proof steps. And we also have a software called Factom at TU Munich, in which we can actually model an architecture, connect inputs and outputs, and also write the contracts for each of the components. And from this, we translate directly to APML code. And at a later stage, APML code is then translated to Isabel, so the language of the interactive theorem prover. And how that works is like this. First, we have a pattern name for which we declare local in Isabel. And then we take all the sorts, operations, and predicates declared in APML, and we translate them to fixes. Then we take all the contracts and we create assumptions for those. Note here that every assumption has a name so that we can refer to those later in the proof. And then we take the architecture contract and create a theorem out of that. So for example, in our case, we have theorem sum, and it assumes that we have for input 1 at time point 0 equals to x, and then the other input equals to y. And we want to show that the merger output is equal to x plus y. And then from the proof steps, we create the overall proof. So here we have a kind of a bit more complicated algorithm compared to the other ones, but it's, because we have multiple cases that we need to handle in order to come up with a code translation like this. We also did a case study in which our main goal was to show that can a person with no prior knowledge in formal methods and also in interactive theorem proving come up with contracts, proof steps, and architecture proofs. So we took a real-life project that is a project actually from a partner from TOM, and what the project was about is that they built an automatic train control system for metros, rapid transits, commuters, and light rail systems. So basically the platform doors that you might find in front of a train to protect, to add additional protection for users. And the focus here was to verify the key features, so the control of the platform screen doors. And our subject didn't have prior knowledge in formal methods, and in general also no knowledge in interactive theorem proving. So as a setup, we had documents, we had high-level documents, detailed ones, performance specification, and also a glossary. And the overall architecture had 33 components, in which the subject came up with 36 contracts in total. And for the results, we had 5 scenarios which we wanted to prove. and the subject spent in total 25 working hours in coming up with all the proof steps. And here you can see the number of proof steps which it requires for the subject to write for the different scenarios. For example, for scenario 1, in which we wanted to prove that if the train is moving, the PSDs are closed, the subject had to write 15 proof steps. For these two other scenarios, these were rather easy, so he had to write only one proof step for each. And then these two were again a bit longer, so for these he had to write 14 proof steps for each. And with that, I'll come to the conclusion. So what did we do? We aimed to close the gap between users and interactive theorem provers to verify software systems. And we introduced APML, which is an architecture proof modeling language, which allows to model proofs in a message sequence diagram approach. And for this we provided definition, soundness and completeness, and did a case study on a real-life project. And what our case study showed is that it showed that APML indeed contributes to the overall goal to bridge the gap between users and interactive theorem provers. Beside the good results that the case study yielded for us, it also yielded some limitations. And one of the limitations is that the expressiveness of our notion of contracts is rather limited. So there are some limits for the notion of our contract. For example, we cannot have contracts with multiple guarantees that happen at different time points, or that can have an interval for their duration. So one of our future work will be in this regard. Then another limitation that we have is that for some of the scenarios, for example, if you look at the scenario 4 and 5, these were quite similar to one another, and their sequence of proof steps were quite similar to one another. So currently we don't have a way how we can reuse such sequences. So the user basically has to copy-paste those, and that's of course not good for maintaining. So that's also a future work for us. And as a third limitation is that it's rather in the level of the interactive theorem provers. So Isabel has some limitations, and because of those, then the user still needs to do some manual work, and our aim is to do automation in this level. And that was it. Thank you very much, and I'm open for questions.
So there are